now going to pass to Gabi Hegerl, who's a climate scientist from Edinburgh, has been working in the IPCC. I've known Gabi for years, so it's a pleasure for me to introduce her. And I'll give you a little secret that she's a very keen rower, and I see her often on Facebook, somewhere off Dunbar in a boat. Gabi, over to you.
Thank you, David. That was a nice thing to add. Okay, so I'm going to try to share my screen now, which is always an exciting adventure. So thanks, David. And it was really fascinating to hear about how COP works, which is still a mystery to me. I have been involved in the Intergovernmental Panel on Climate Change, and they're in plenaries that approve the report, which gives one a little bit of a taste of that, but it's still a different kind of thing if it goes to the political solutions to climate change. So I'm going to talk both a little bit about our own research and a little bit about the report that just came out from the Intergovernmental Panel on Climate Change. This time I was a review editor, which is basically a person who looks at the review comments received on a chapter and helps the chapter and helps and ensures that the chapter addresses them well. So I was a bit peripheral this time and a bit more involved in previous years. It was quite interesting to watch them do their work by Zoom, which is a very big change if you need to build consensus, but they have been very successful in it. Before I start, I would like to mention that many of you might have heard yesterday that the Nobel Prize in Physics went actually to two climate scientists and a physicist working on chaos. And the two climate scientists are both, one is 90 and one is almost 90. Klaus Hasselmann was my postdoc supervisor, and I couldn't agree more with the choice of those two people that the panel has made. It also, with that, has also made a point that climate physics is physics, which we have been saying all along, but there has been some discussion if this is a niche field or a really important fundamental field. And I think understanding how the planet works and how the climate of the planet sets itself is a really important thing to do. So it's really nice that it was recognized in that way. And I also show you their pictures because their work flows into some of the things I'm going to talk about. So this is a slide from the Met Office that shows how global mean temperature has evolved over the instrumental period, so the period when we have enough observations to calculate global mean temperature. It is shown as differences from a long-term mean. So each station, for each station you calculate the long-term mean of that station, and then you calculate if an individual year is warmer or colder than average, and then you average them all up to get the global mean temperature. And you can see that there's a lot of variations. This slide doesn't add a time axis, but the pre-instrumental period, basically, or pre-industrial period, which is really a proxy for the pre-industrial period. An estimate is 1850 to 1900. So this is the base level that we compare our present warming against. So these are basically where you can see the graph kind of being both blue and yellow, and then you can see a very strong warming up to the 1940s approximately, and then a flat period, and then the very strong warming into the present time, and this graph goes to 2020. The choice, if you want to hear scientists sound like discussing angels on a pinhead, the choice of pre-industrial period is something that can get people very excited. It is quite tricky to find out what pre-industrial climate actually is like. I think the fundamental argument is that when we defined what is a safe level of climate change, we also the work that has gone into has used this late 19th century baseline, and therefore this is an appropriate baseline, even if we recognize, including by the work in my own group, that by 1900 we already had some greenhouse warming in the atmosphere. So the recent warming is quite dramatic in that context, and that is not just limited to warming of the surface air temperature, but as shown in this quite nice diagram from the IPCC in the chapter I was a review editor for, is this change in climate goes through components of the climate system. So if you look at at the CO2 concentration, which we know has increased very dramatically, and we are now far above 400. We also see some changes in rainfall, and for Scotland, I think particularly interesting is the change in Northern Hemisphere land temperature. And so in temperate latitudes, and you can see basically a greening of that plot over time. So compared to the pre-1950 periods, we are quite wet right now, and that is consistent with what we expect from climate physics. We also can observe that glaciers have lost mass pretty much everywhere, and in some regions are really beyond salvation, or beyond hope of coming back. So some of the alpine glaciers are in quite in the Alps are in quite bad trouble. We have seen the warming seen in the plot before. Sea level has increased, both observed by satellite data and before then by some stations, and we can push that back in time if we use long-term station observations. Ocean heat content has warmed, and this is a data set that is again based on instrument data and augmented in that case by a model. So the key message from that plot is that everything is changing, and we are not dependent on a single data set to tell us that climate is changing, but it is a change that's going across the system, and a change that is even visible in some sense directly if we look, for example, at glacier pictures, looking at where the glacier is now compared to where it used to be. So the IPCC key message is that it is unequivocal that human influence has warmed the atmosphere, ocean, and land, and that we are looking at widespread changes. This is a very strong increase in statement compared to the previous report released in 2013, because it is not only unequivocal that it's warming, but that the warming is due to human influence. And I think it's very appropriate choice of statement, because we have really seen a lot of increase in evidence. One of the interesting lines of evidence, and a very new one, is that we now have global mean temperature reconstructed since over the Common Era, so since 1 AD approximately. And so that's that gray big uncertainty line showing temperatures evolving up to the period when instrumental data started, or a global instrumental data set started, and then you can see the global instrumental data set recording the proxy data together, recording the observed recent warming. And so this is a quite dramatic graph, and it is based, the reconstructions are based on, for example, tree ring data, ice core data, documentary evidence, a multitude of data sets. It now includes the Southern Hemisphere, which is a massive advance, and that has been made in paleoclimate. And you can see that over the period of the record, temperatures are slowly going down. That seems to be an interesting combination of changes in the statistics of volcanic eruptions, orbital forcing, some solar influence, although that seems to be relatively small in that case. And then you can see the observed recent period really shooting up very sharply. And the conclusion is that human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. And there's a bar indicating that we are also emerging from the range of warm multi-century periods in more than 100,000 years. So it's a bit more tricky to compare multi-century periods to trends. So that is, but what is very clear is that the trend over the instrumental period is very extreme compared to what we have ever observed before. The reconstructions really process uncertainty carefully, including in the reconstruction method. So it's quite a nice tool. And then on the right-hand side, you can see that over the instrumental period, 1850 to present time, the observations in black can only be reproduced if your climate model, which is the orange and green shaded lines with the envelopes that represent uncertainty. You can only represent the instrumental data if you include both human and natural influences on climate. Natural influences on climate are interesting and important. You can see the in the green and also in the combined human and natural, you can see the sharp drops, for example, that follow large volcanic eruptions. So they are not negligible, but the driver of the upwards trend is clearly human influence. And now I want to show you how we estimate how much of the warming is due to humans. So this is a graph again from the summary for policymakers, where the observed change in temperature is shown since from 1850, from the pre-industrial proxy baseline onwards. And you can see that we estimate that we have now exceeded 1 degree of warming with some uncertainty, a relatively small uncertainty. And now we look at why we have warmed that much. And the first approach to estimate that is to use patterns of warming expected from climate models and then looked for in observations. This is a method that has been developed and proposed by Klaus Hasselmann, by one of the Nobel laureates. I think it is not his biggest achievement, but a really nice achievement of him. And I have had the honor to implement it in observations together with another scientist, Ben Sante in Livermore. So we were both working on that topic, and it's still used to estimate how much of the very noisy and busy observations show a signal of observed of greenhouse gas increases or other influences such as aerosols or natural forcings. So the estimate based on these methods indicates, and those methods account for uncertainty in how strongly the climate system responds. So they allow the observations to determine how much warming do you get in response to greenhouse gases. You tell the observations you're looking for a global warming pattern that has land warming more than the oceans, that has Arctic amplification, and then you apply a noise reducing metric and find that this is the amount of warming due to greenhouse gases. So for example, greenhouse gases have, based on these estimates, caused more warming than observed, with uncertainties offset to some extent by other human drivers, particularly aerosol. In combination, the human drivers explain pretty much exactly the observed warming, and the role of solar and internal variability is small to the long-term warming trend. It gets larger when you look at shorter time variations. And then the second comparison you can make and approach you can make to explain the observations is to look at what we call radiative forcing, of how much different trace gases influence the atmosphere. This is very much based on the work of the other Nobel laureate for climate, Suki Manabe, who has been working on climate modeling and on understanding how different gases in the atmosphere change the atmospheric structure and the planet's energy budget. So this is really nice. This diagram connects both laureates in a very nice way, and you can see that different greenhouse gases have estimated to contribute different amounts. They've also looked at aviation, contrails, all kinds of other things, land use change, and vegetation change, which has caused net cooling on an estimate due to less absorption if you have grassland rather than forest. So both of them agree that greenhouse gases, so carbon dioxide, methane, and nitrous oxide combined, explain more than the observed warming, and some of it has been offset by other factors. When we look at the observed warming here on the graph in the top middle, you can see that the pattern of warming that we have observed, which reflects the fingerprint method as well, is very similar to what we expect from climate models at 1 degree of global warming, and in shape very similar to what we expect to go forward as we go. If we go to 1.5 or 4 degrees. So you still see a warming more over land than over ocean, because the land has less heat capacity. You see a strong Arctic amplification, which we also see in paleoclimate records in periods when the climate changed. And we can see, so this kind of pattern is already very evident in observations. And we just get more warming as we move to higher levels of global mean warming. This also affects rainfall, but it's a bit trickier to see observed rainfall changes showing already that signal, because rainfall is so highly variable. I think we all know that it varies from year to year, and we can have a rainy or a wonderful summer. We can have, and the wonderful summer that is dry might also bother the farmers. So it is a tricky, rain is a tricky bit. The plot not only shows rainfall, but it also shows changes in column soil moisture change. That is a measure of drought, which is slightly different. The colors there are slightly different, because drought is not only caused by changes in rainfall, but also by changes in evaporation. And that again links to heat. So if you have the exact same rainfall amount, but heat the planet, you will still get an increase in drought due to stronger evaporation. And my own group, we contributed a figure to the IPCC report. This is the figure that isn't in the report because we plotted together the observations and the future. The report figure goes up to here, and you can see that wet regions in the tropics are getting wetter in satellite data over the tropics and subtropics, and dry regions are getting maybe slightly drier, but that's a much more noisy signal, and it's in line with what we expect from models at the present time and into the future. It only works if you look for the rain. So if you follow the rain and aggregate the wet regions together and the dry regions together. Climate change also strongly affects extreme events, and the IPCC has done a very strong and very good job in documenting this. These are some pictures from extreme events that are no longer the most recent ones. I apologize for the bottom right diagram. This is, I think it is sad and necessary. It's flying foxes. So those are mammals that cannot withstand temperatures above a certain level. Lots of mammals are like this. We humans also have a human threshold above which we get very uncomfortable and then eventually are in serious danger. And so this happened in Australian heat waves, that the flying foxes fell out of the trees dead because they could not withstand the temperatures anymore. So the IPCC has a very nice diagram, I think, aggregating different regions and looking at what kinds of extreme events have changed. And the top diagram is heat events. So this is basically looking, when we look at what they call here NEU, Northern Europe, that includes actually Scotland, whereas Western Europe includes England, which is and the splitting line is somewhere in the middle of England. So for us applies Northern Europe, and we can see that we have an increase shown in red in observed changes in heat. We also have a high confidence that this is due to human influence. That's what we call attribution. And that kind of level of confidence applies to almost everywhere on the globe, with small exceptions. Central Africa doesn't have enough data, and as Southern South America. And there are some regions, Central and Eastern North America, where the trend over the instrumental period is not very pronounced. And that is a really interesting area where my own research has gone, where the record heat has actually occurred in the 1930s. And where in the moment we don't see a strong heating, and there's my research suggests that there is an involvement of the land surface and vegetation, and also possibly irrigation here. So there are very small exceptions, and there are interesting case studies in what else influences temperatures. Then when we go to extreme precipitation, we see less green, which indicates less regions where we have a significant and robust change in the observations. But Northern Europe again has an increase, and that is where there's high confidence is due to humans. But you can see that that's a bit more widespread, a bit more spotty across the globe, because rainfall is so much more noisy. And then when we go to drought, we can see an observed change, and I'm losing my cursor here. We can see an observed change that is significant and robust in some regions, particularly Southeastern Africa, parts of Africa, also the Mediterranean, and there's actually quite and Western North America. And there is a medium confidence that the change in the Mediterranean and Western North America in drought is due to human influences. Those droughts have had a quite significant impact, particularly Western North America is quite concerned about drought, and it impacts a lot of aspects of life there. The IPCC has also concluded that these extreme events are expected to increase even further in the future, and their frequency and intensity is expected to go up quite dramatically. And there are some nice figures on that, but I didn't want to cause death by PowerPoint showing lots of very technical figures. And so I would rather go to two extreme events we have recently observed, just as a case study or as what may happen. So we have, I think everybody has followed the terrible news of the European floods of this summer, which caused a very high number of fatalities in Germany, some very tragic cases, including people in a care home for handicapped people, and 38 in Belgium. The meteorological system linked to this was a cut-off low-pressure system, and there was very heavy rain on saturated soil and very complex terrain. And the World Weather Attribution Project, which is a project that is led by Friederike Otto and Gert-Jan von Oldenburg, estimates, they can do very rapid studies using established techniques to estimate within a few days if an event that has occurred is due to natural variability or due to management or something else, or if it has really been influenced by human influences. And so in that case, in that specific case, they estimate that this was an extremely rare event on the River Aar, and that human influence have increased the probability of such heavy rain, but with quite a bit of an uncertainty range how large that human increase is. The floods, anybody who has listened to the Life Scientific, which I'm a big fan of on Radio 4, has heard Hannah Cloak discuss some of these events, and they have been predicted. So there should have been warning in place, but the warning did not work, possibly because the event was so far out of the experience or recent experience of the planners and also the population that they were just not acting on it. So I think this case highlights very strongly that we need to think about adaptation and how to involve society and decision makers in these adaptation decisions and how to make them actually stick. Because as we increase greenhouse gases in the atmosphere further, we get more, the atmosphere gets moister, and if you have the right conditions for extreme rain, you get more of it. Another extreme case were some heat events this summer. So there was this heat dome case in the Western North America, which was a very extreme meteorological situation, a very strong high pressure system causing very intense heat over a region that does get nice summers, but not that extreme conditions under normally. I've lived in Seattle for 2 years doing a postdoc, and the temperatures that they have reported there were very different from anything you would have expected in that region. So the temperatures were far above 40 degrees. They had to have cooling rooms for the population in Portland, as shown in the picture. There were spikes in deaths and hospital visits. Heat waves are some of the most deadly disasters. The World Weather Attribution again estimates that those temperatures were virtually impossible without human influences. And in the same month, Jacobabad in Pakistan recorded 52.8 degrees. And those are temperatures that are definitely extremely dangerous for humans. So when we think about COP, I think we need to think that there are some events and some changes that humans cannot adapt to, and that are causing huge challenges for both humans, wildlife, the ecosystem, and agriculture. So we have to, if we want to avoid events like this getting much more frequent and much more dangerous, we have to really also mitigate very strongly and limit the level of warming. The Intergovernmental Panel on Climate Change is also plotted forward into 2100 and for sea level to 2300, which is shown on this kind of busy plot, which shows the different scenarios. I would like to draw your attention only to a few things on this plot. First off, the lowest emission scenario, which has a very technical name, exceeds 1.5 degrees and then comes back down to it. So this is basically a scenario that we could long-term reach 1.5 degrees of warming if we were to follow it, whereas the highest scenario reaches about 5 degrees global mean warming at the end of the century. This in the high scenario leads to a complete loss of Arctic sea ice, very strong change in ocean acidity, and all of these scenarios have a limited level of sea level rise up to 1 meter, and the IPCC has this time also used a high-risk storyline of what happens if sea level responds much faster than we expect. So it's a physically plausible but not likely scenario that is used for planning for the worst case scenario, which I think is really important to consider as well. But then if you go with sea level to 2300, you then are looking at very scary numbers of sea level also for many coastal cities. If we go for the high warming scenario, if we go for the low warming scenario, we still reach problematic levels. And that's the text that the IPCC made on that. We should be also concerned about things we cannot fully predict, and that's there's a bit of work on tipping points in the IPCC and also in the research community. So I'm co-leading a research, an activity of the World Climate Research Program on safe landing climates, which is explicitly also looking at the danger of irreversible change or tipping points. And so examples of tipping points could be, for example, that drought in the Amazon, for example, could cause a sudden dieback of the Amazonian rainforest from which it cannot come back easily. And this is exemplified in that kind of little probability diagram where we are presently in a climate state where we have a forested Amazon. And if a drought pushes climate over this little hump, you wind up in a climate state where you are in an unforested one, and where it is quite tricky to get back to the previous state. So it's not just, you don't move. So if you kill off the trees, you don't straightforwardly move back to the trees regrowing, because the weather conditions around you change and it's not so easy to grow them back. That's more extreme even for the Greenland ice sheet. If you melt the Greenland ice sheet, you change its reflectivity and it doesn't grow back under the same conditions. And that's kind of a tipping point where you change the entire climate state, as is the thermal highland circulation. So the IPCC considers those tipping points, but it is still not very well understood, and in many cases involves complex interactions between humans, sometimes between aspects of the climate change that react at different timescales. So it's tricky. An example for me of a tipping point were these Dust Bowl heat wave and droughts in the US, when we had, due to very strong drought, but also human influences by cutting, by plowing up the prairies and trying to grow wheat, which was successful while the rain lasted, and then very unsuccessful. There was a change in the land surface in the Great Prairies that was very hard to reverse, and it caused very severe impacts that are described in the Nobel, The Grapes of Wrath. So basically all that this shows is that we are looking at a quite dangerous world if we go above our 1.5 degrees. And if we look at the historical warming, if we plot the cumulative total emitted CO2 against the temperature that we have observed, we can see from observations that they are following on a line, and this same is true for the scenarios. And so this is where the net zero comes from. If we want to limit global warming to, for example, 1.5 degrees, we have to limit the total aggregated emissions, which means we have only a little bit of emissions left to actually avoid exceeding our threshold of 1.5 and also 2 degrees. And so the IPCC has given us some numbers, and these numbers are quite small. So we don't have a lot of carbon emissions left before we commit to a very severe warming. So the conclusion, the first climate models still stand up in the fundamental properties of global temperature. The key message has been the same for many IPCC reports, but it has strengthened over time, and we are all experiencing impacts of climate change, which should really motivate us to both think very seriously about mitigating further climate change. As a scientist, I can only tell society that these are our options. As a mother, I'm very much hoping that we are successful in mitigating climate change, because I'm quite frightened of what would lie ahead if we don't. Thank you.
Right, thank you very much, Gabi. That's a good overview of the whole of the Working Group 1A area. I've got quite a few questions coming in. I've been trying to answer a few directly, but some for Gabi, first of all. Chris Nick suggests, can we address the extreme events, floods, tropical cyclones, etc., to climate change in a scientific manner which the public could be convinced?
So there is a lot of work going on, and the people I mentioned, Friedi Otto and Gert-Jan von Oldenburg, were nominated as were listed as the 100 most influential people by Times Magazine for doing exactly that. So they use different methods. So they use the observations and see what part of the observed trend is due to human influences. They use the models and see what would this event have looked like in the past without human influences. They get quite strong messages. You also have really physics on your side. So for example, if you look at an extreme rainfall event and the same event in a less warm and therefore less moist atmosphere would just not have as much water vapor available to rain so hard. So if you have the exact same kind of rain event happening, that in the present time it will rain harder if it's right for rainy conditions. If it is a heat wave event, the warmer atmosphere overall will make the heat more intense, and then eventually feedbacks kick in, such as the soil dries out, and so we look at very dry and very intense heat. So it's I think we are in a good position to answer these questions about some events. There are also complex events, like drought can be very complex, and the results. And if you look at past droughts, it's quite tricky to determine if it's a human influence. The strongest statement I've seen is the Cape Town Day Zero, which is in a region where we exactly expect that kind of drought and dry conditions to occur more frequently in the future. That was also a quite problematic event where Cape Town looked like it was possibly going to run out of water.
Now, here's an interesting one. Rosemary Cantwell asks, have climate change scientists investigated the impact of the internet? And what about blockchains, the warming attributable to such massive reliance on computers worldwide, etc.?
So computers use a lot of energy. That is an interesting question, how we power them. I think there was the supercomputing centers that run also climate models use a lot of power, but the direct warming from, for example, from them is not is a very small factor. Did I understand the question correctly?
I think so. Yes, I think though the whole blockchain issue is probably one which has not been looked at much. I mean, I gather that some of the blockchain processors have emissions that are almost the same as small countries. So
yes, it is a huge. So if we decarbonize our energy sector, this is less of an issue. But we need to decarbonize the energy sector, which is far out of my expertise. But but energy generation, particularly if it employs coal or gas, it will more so for coal than gas. It does produce a lot of emissions, while wind power or solar power does not so much.
okay. Just watching the time. There was another question that I was going to pass your way. Yes, David Stevenson asked, can we attribute extreme events to particular gases in some way? So we can attribute average change in temperature to different gases. Can we, or is, I mean, I guess it might just be pro rata, but what's your view on that?
That's an interesting question. We could do it pro rata, as you say. We could for some trace gas, like or they are not trace. For the aerosols, it is actually possible because they cause a different and a more localized impact. So you can, for example, attribute some monsoon changes over long-term periods to increases in aerosols. And also the Sahel drought has been partly in the 80s has been partly linked to aerosol patterns. But if you go for is this heat event, how much of this heat event was caused by greenhouse gas versus methane increases, then it's quite tricky because they mix well and do the same thing to the atmosphere. So you would have to do it pro rata.
Yes. Okay. Thank you. Then somebody has asked about volcanic and seismic activity. Is that any sign that that is changing due to loss of ice sheets, for example?
So loss of ice sheets would change seismic activity, but I haven't heard much that that's already a big factor. They are starting to merit. We now see their contributions to sea level, and I'm sure we'll hear more about it this afternoon. But they are it's still a relatively small factor. But the big ice sheets do change, have an impact on the geology of the planet, and so it's probably going to be measurable, and possibly there are already measurements that I don't know about.
Yes. Okay. Well, thank you very much. And thank you for the questions to Gabi. There's a few questions to me, actually, which I probably just take the opportunity to answer now. Hugo Talbot, to what extent are global carbon budgets expected to be part of the negotiations at COP26? Well, what I would say, it's part of the underpinning part of the whole process. I don't think countries will be negotiating carbon budgets as such, but knowing what the carbon budgets actually are from the IPCC report guides what emission reductions countries will need to make. So we know we're looking at something like 45% reduction in global emissions by 2030 is required. And we're nowhere near that at the moment. So I think that'll be the driver for change. Just see what other questions. Debbie Bassett says, I presume the UK is in the G77. Actually, it's not. The UK is definitely seen as a developed country. But the question is, who are we lining up with at COP26? I think that's an interesting question. We're now out of the EU, so we're no longer part of the EU process directly. But I'm not aware that the UK has formally aligned with, say, the umbrella group, which in theory it could do. But because it's the presidency this year, it may want to leave that to a future meeting. But something to watch, I think. Debbie also asked about the role OPEC plays in negotiations. Well, OPEC, they're an observer. There are the countries that are in OPEC actually coordinate as a group. So they're very much an influence behind the scenes. As to renewable energy suppliers, quite a lot of industry groups, and this goes to another question that was asked, are actually observers at the convention. And of course, they can work through their own governments in terms of gaining influence. In fact, one of the things the industry people who do go to is they'll be lobbying governments and groups all the time. So I don't think I can immediately answer that specifically. No one industry group actually is represented in the negotiations per se, but they are there present and they can talk to people and they can influence people. I think it's probably the way to put it. Vicky Ingram asked if finance is available for less developing countries, they should be improving data collection. There is a strand in the finance package that recognizes the importance of improving data collection. But I have to say it probably plays second fiddle to things like funding for adaptation and mitigation and stopping deforestation. But I think in principle it could be done. And certainly there is a big gap in quite a lot of countries, not just Africa, but in other countries, perhaps in Asia and South America, where data could be considerably improved. Yes, the last point from Jody Ireland, I feel the climate change is very scary and I try to do everything I can to help, but I feel it needs to be made easier for people to make better choices. Is this a major factor? Well, I think this is something which governments really have to bite the bullet on. There's so much that people can do as individuals, but if it's structural changes in society, really it's governments that have to act. And there's two things there are things which governments are directly responsible for, say the electricity generating system, for example. But if you think about the big change that's going to happen domestically in people's houses, moving from gas boilers to heat pumps or something similar, in a very short time, it's a big challenge for government to decide how best to do this, supporting people, but at the same time making sure that public finances are not totally, letting people off the hook in things that they could do themselves. So I think that there's going to be a big challenge in designing the way in which people individually are incentivized to make changes, particularly in their houses. Gabi, you want to?
Yeah, I really like your answer on this question, which is a really important question. I think because it is important that we all do our bit, but the big thing is that the governments need to set the framework. And so we as individuals have to make decisions. And even if we are very concerned about climate change, sometimes we emit carbon. I do that as well all the time. We should be just aware of what we emit. But I think the important thing is that we need to support the governments to make the decisions we need to do to address climate change. And it's really in their hands to change our, particularly the CO2 emissions from power generations. That is not something we can do. And we shouldn't be pushed as individuals into the corner that it's us who has to do this alone. That is a very dangerous way of thinking about climate change.